Hi guys, me again. Hope you guys are doing well and had a good spring break, finger quotes, spring break. I know it wasn't the typical break that we all wanted, but at least there was no new schoolwork. So I hope it was all good and everybody is still doing well. I feel like I look all crazy because I'm sitting in front of the window in my bedroom. I feel like I look very washed out. So I apologize for that. I've got like weird light coming at me in all different directions. But I am going to start talking about the next unit this week. You guys will have a Alex thing to do. We decided to just, instead of doing like a big test, because we're still a little fuzzy on like giving tests and all that. So I think what most people are doing, I don't know, I say that, but maybe it's just most of the math teachers, I don't know, are just giving like quizzes. So that's what we decided to do. Since you guys already had a quiz over the first half of the polar unit, you did all the graphing and we had a quiz. Which, by the way, I think there's still like 2 people that need to make that up. So if you feel like you are one of those 2 people, I won't necessarily say who they are here, but if you feel like you are one of those 2 people, send me an email. But anyway, you did the graphing, had a quiz on that. The second half was all the stuff that we've done since we left school. So it was like the converting, basically the other 2 videos, right? So like converting into like with complex polar form, we talked about how to go back and forth between those different forms and get the R value and the theta and all that. And then we talked about how to multiply 2 of them together and divide them. And then what was the other thing? Raise it to a power, right? That was that de Moivre's theorem. So that's the kind of stuff that was in the second half of the unit. And that's what's going to be on your Alex quiz this week. So you guys will have that quiz to do. And then this video to watch. But there's not going to be any extra homework attached to this video. I'm just going to sort of give you some general notes to kind of introduce this unit. But really in terms of like the actual work that you guys will do this week, it's just the Alex quiz. So that's that. Okay, I feel like I was going to say something else. And now I can't remember what it was. I feel like I do that a lot. Okay, anyway, let's get started. I'm gonna switch over so I can give you guys some notes, and then a little bit later on, I'm gonna switch over to Desmos and show you some stuff. So let me give you a little background. So this unit that we are gonna be working on for the next couple of weeks, probably 3-ish, maybe, I don't know, is sequences and series. So there are general sequences and series, which is what we're going to talk about today. Today's a lot of just vocabulary and just kind of presenting the concept of like, what is a sequence and what is a series? But then after today, after this video, then the next 2 videos will go into more specific types. There's 2 in particular that we're going to talk about: an arithmetic sequence / series and a geometric. So you guys may have come across these in past math classes. I feel like maybe in Algebra 1, there's a little bit of sequence and series stuff. I could be wrong, but you might have sort of gone over some of this. There might be some little nuggets in there that you kind of like, oh, I kind of think I remember that. So that's sort of the plan, but today is just sort of general stuff. Like I said, a lot of vocabulary and stuff like that. Okay, so let me switch over and we'll get started. Okay, let me make this big. Don't need to see me hide myself up here. Okay, so let me grab my stuff here. All right, so we're going to talk about sort of 3 concepts in today's video. So we've got sequences, series, and sigma notation. So I am switching it up today. I'm doing this from my bedroom instead of my kitchen. So I'm writing on the carpet, as you can see, which is not as nice as writing on a hard surface. Also, you saw my my Tigger ears. I know you're probably at this point wondering, how many of those things does she have, right? So I guess you'll find out. Anyway, a sequence, let's start with a sequence. So a sequence is just an ordered list of numbers, pretty basic. Kind of what you probably thought it was going to be. An ordered list of numbers. Okay, ordered list of numbers. Hopefully you guys can see this. So a sequence can be infinite, which means it will go on forever. Our list of numbers can just continue on and on and on and on and on, infinite, or it can be the opposite of that, which is finite. So these can be infinite or finite. And then another little piece of vocab, each number in the sequence is called a, kind of running out of room here, is called a term. So I could, talk about the first term or the second term or whatever. Okay, so we're going to talk about 2 different ways to define a sequence. So usually when you're talking about a sequence or a series, there will be what I call like a rule or a formula so that you can calculate the terms in the sequence or the series. So we're going to talk about 2 ways to do that, 2 ways to give the formula or the rule. So the first thing we're going to jot down is to define a unique sequence, a formula or a rule must be given. So for instance, we'll look at an example. You'll see notation that might look like this. So this is our rule. So we have to sort of talk about what this notation means. So you might see something like this, and then the directions might say, find the first 4 terms of the sequence. So unless it's otherwise stated, when you're finding the first 4 terms of the sequence, like in this case, or finding the first however many terms, you are going to start, because we're going to be plugging a number in for our variable here and then working it out, right? So it would just be kind of the same as if you were going to like graph something and you had to plot some points, right? You have to have a number to plug in. You have to have an X value to plug in. Well, here we don't have an X value. We have an N value. So we would be plugging values into this variable n, into that spot, and working it out. And unless it's otherwise stated, we typically start with 1. So we would come down here, and so this notation, this a sub n, you'll see that a lot when you're doing stuff with sequences and series. It just means like n is our term number, and it's also our variable over here. So whatever we plug in for this n is also going to be the same number that we plug in over here, because this n and this n are kind of the same thing, right? So if I come down here and I say, okay, I want to find the first 4 terms, I want to find a sub 1, a sub 2, a sub 3, a sub 4. So then that means that I'm going to take this one, because remember, whatever number I put here is my subscript, that's the same number that has to get plugged in over here. So 1 is my subscript, so that means that I'm plugging in a 1, and then I'm plugging in a 2, and then I'm plugging in a 3, and then a 4. And we just kind of work out what all of those are. So I'm going to get 1, 4, 7, and 10, I believe. So this particular way that I've done this, where I've basically just given you a formula and you just plug numbers in, this is one way that you can define a sequence. So this is sometimes called an explicit formula, or defining a sequence explicitly. So an explicit formula, or defining a sequence explicitly. So that's one of our types, or one of our ways that we can define a sequence. We can define it explicitly by just flat out like saying, hey, here's the rule, and you're going to plug these numbers into this rule. So there's another way that we're going to talk about in a second, called a recursive definition. So that's a little bit different. So we have explicit definition or explicit formula, and then we'll have recursive. So I'm going to give you a couple to do on your own if you want just some practice. So same directions. We're going to find the first 4 terms of each sequence. So I'm going to give you 2 explicit formulas. So for the first one, we have a sub n equals -2 to the n minus 1. So again, you want to find a1, a2, a3, a4. You don't necessarily have to write out the rule every single time like I did up here. Most of these you can probably just kind of do in your head. I'm going to write out just like the first couple here just so you can sort of see what's going on. But remember, whatever number we put here as our subscript, that's going to be the same number that's got to go in over here in this n as well. So that means this is going to be -2 to the 1 minus 1. This is going to be -2 raised to the 2 minus 1, and so on. So 1 minus 1 is 0. Anything to the 0 power is just going to be 1. Let's say 2 minus 1 is 1. So -2 to the first power is just -2. And if you want to stop the video and kind of figure out the other 2, you can do that. Let me give you another one to think about over here. That way you can kind of do both of these at the same time if you want. A sub n equals 3 plus -1 to the n. So if you want to stop the video for a second and see if you can find the first 4 terms of those, and then come back and check your answers. All right, so we did the first two over here. So the other two, when you work all of this out, you should get, for the third term, you should get a 4 and then a -8. So notice your sign is kind of bouncing back and forth between positive and negative, because we're going to have this negative number raised to an even power and then an odd power and then an even power and then an odd power. So our signs are going to bounce back and forth. Over here, we figure out these 4 terms. I got 2 and then 4 and then 2 and then 4. And then presumably that might continue on if we were to keep going. I'll give you another sort of thing to work on. Just, this is sort of an optional thing if you want. I don't really spend a ton of time on this type of problem, just because I've kind of found in the past after teaching this for several years that some students are really good at these and some students are just terrible at these, and it causes a lot of stress and anxiety for them. So this is more just like a brain teaser sort of thing. So I'm only sort of throwing these in just like as a for fun kind of thing, but you can sort of go the other way with it. You can start with sort of the end result, the end numbers, and then figure out like what was the rule that gave those values. Does that make sense? So we'll say for these, write a rule for the given sequence. And again, you know, this is kind of just a kind of brain teaser for fun thing. I don't generally like throw these into quizzes and tests and stuff like that because, like I said, some people, these are really easy and they're like, oh, I got it, and they figure out the rule really quickly, and then other people can just sort of stare at it all day and it just never happens for them. So, you know, it's kind of a mixed bag. So for that reason, I kind of don't put them on assessments, but I do sort of throw them into the notes. So I'm going to give you the sequences, and well, here, let me write these out first and then I'll give you a little bit more info. So the first one is 1, 3, 5, 7, and then it would continue on like that. B, we have 2, 5, 10, 17. Then C, we have E squared over 2, E cubed over 3, E to the 4th over 4, and so on. And then I'll squeeze in one more down here. We have 1, 1/3, 1/9, 1/27, and so on. So the assumption, one assumption is that when you are thinking about your rule, if you're sort of thinking about it, you know, what we did up here, and you're sort of trying to go backwards and figuring out the rule, we're going to have the same assumption that we used up here, which is that when we're thinking about plugging numbers in, we're going to assume that we're starting with 1. So you can think about that as you're thinking about these down here, that you plugged, like say for part B, we're thinking about a rule that we could plug 1 into, and then when we evaluate it, we get 2. If we plug in 2 and we evaluate it, we get 5. If we plug in 3 and we evaluate it, we get 10, and so on. So again, if you want to sort of stop the video and see if you can play around with those, some are a little easier than others, and see what you come up with, and then come back and you can see if you got it right. So I'm going to come over here and give you all of the answers. Okay, so for the first one, 1, 3, 5, and 7, our rule is 2n minus 1. Next one is n squared plus 1. Then we have e to the n over n. And then we have 1 over 3 to the n minus 1. Now, if you didn't use n, that's okay. If you came up with a formula and you used x or whatever, that's fine. The variable doesn't really matter. But that is the rule for each one of those. Okay, and again, that's just kind of a for fun thing. Okay, so let's talk about the other type of definition. So this first type that we did up here, explicit definition. We just give the formula, we plug the numbers in, we work it out, right? That's explicit. The other type is recursive, recursively defined. Recursively defined. All right. So recursive is a little bit different. With a recursive definition, you get a couple of different things. So this is going to give the first term or the first few terms, and then the following terms are based on those first few. And I know that that is kind of a weird definition, but it'll make more sense when you see an example, okay? So come down here. All right, so I'm gonna write one of these out, but then I'm gonna come over to the side over here and give you a little bit of notation stuff before we kind of jump into this one. So if I define something recursively, typically what happens is I will tell you what the first term is, or maybe the first two terms, and then I'll tell you a rule or a formula for how to get the next term based on that first one. So what that would look like is I would have to say, okay, the first term, a sub 1, is something, whatever it is. Let's say the first term is 1. And then I would have to tell you that the next term, or the nth term, can be gotten, this is a with a subscript of n minus 1. Okay, so we need to come over to the side over here, and I need to sort of give us some notation, okay? So a sub n, we'll refer to that as the nth term. So like that means if this is a 1, then we have the first term. If this is a 2, it's the second term. If this is a 3, this is the third term, and so on. So this number just tells us what term that is, right? Now, you'll notice we've got this new thing, a with a subscript of n minus 1. So that means that is the term before the nth term. So if this was a 3, a sub 3 would be the third term. If this was a 3 minus 1, that would be the second term. Does that make sense? If this was a 5 up here, a sub 5, that's the fifth term. But if I put 5 down here, 5 minus 1 is 4. So now this is the fourth term. It's the term before the one up here. And then we could kind of keep going with this same notation. Occasionally you might even see a with a subscript of n minus 2. So this is the term that is 2 terms before a sub n. Move that over so you can see that. So a sub n minus 1 means we are just backing up one number in the list. If we have a with a subscript of n minus 2, that means we're backing up two numbers in the list. So if I go back to this example over here, if I want to find, let's say we're going to do the same thing. We want to find the first 4 terms of the sequence. So a sub 1, a sub 2, a sub 3, a sub 4. So we already know a sub 1 because you just kind of told us that, right? So that's easy. So then a sub 2, so remember, if I go back up to my rule, this number that's in this subscript, this n, that's the same number that should be over here. So if I put a 2 for my second term, if that's a 2, then this also has to be a 2. So for my second term, a sub 2, my rule says I have to do 4, and then I've got a with a subscript of 2 minus 1. Well, that's the same thing as just saying 4 times a sub 1, right? So remember, this means the previous term. So this is essentially telling me that I'm taking, that my rule is I've got to do 4 times whatever the previous term is. And that's exactly what this is saying right here. This is 4 times the previous term. If I'm at the second term, a sub 2, the previous term is a sub 1. So I got to look back and see, well, what was that previous term? Okay, so now this becomes 4 times 1, which is just 4. If I go to the next one, a sub 3, don't necessarily have to fill in all of this intermediate stuff. If I just think about it as 4 times the previous term, well, the previous term was 4. So 4 times 4 is going to be 16. And then when I get to the next one, if I do 4 times the previous term, 4 times 16 is 64. And then if I wanted to do the next term, a sub 5, I would do 4 times 64. And I could keep going. We're just doing, the rule just tells us, here's the number you start with. And then to get the next one, just keep multiplying by 4 every single time. Okay? So let's look at another one. Let's say we've got the first term is 1. And then our rule is n times a sub n minus 1. Okay, so we're going to try to do the same thing. I'm going to think about the first 4 terms. So the first term is easy. They just tell us that, so we just fill it in. Now, the second term, again, we've got more places this time that have an n in them. But remember, whatever this value is in our subscript, so for here, for this particular term, it's a 2. So if that's a 2, then that means that there needs to be a 2 here, and there also needs to be a 2 here. All of these n's are the same number. So this means I'm going to have a 2, and then a with a subscript of 2 minus 1. Well, again, if we kind of think about what this means, right, a sub n minus 1, that's just whatever number is like previous in our list. So, and again, I'm going to write this out just so you can kind of see how this works mathematically. 2 minus 1 is 1. So this is really saying 2 times the previous number in our list, right? So here this would be 2 times 1, or 2. But then when we get down to the next number, this is going to be, again, all of these three numbers have to be the same. So now our n is 3. So this is going to be a 3. And then this is going to be 3 minus 1. So this is a 2. Well, a2, we just figured out was a 2. So then again, you could kind of think of it as 3 times the previous number in the list. So 3 times 2 is 6. And then we go to the next one. This is going to be a 4. And then this is going to be the previous term. So let's say previous term was 6. So 4 times 6 give me 24. Okay, let's get one more. So this one's a little different because I'm going to give you the first term and the second term. First term is 1, but the second term is also 1. So we have kind of a repeated value. And then our rule is the previous term plus the next previous term. We're going to add those two together. So that's a little weird. So here I'm going to actually think about going to maybe the 5th term since we're given the first 2. So let's say we want to find the first 5. A4, A5. Okay, so first term we're given, second term we're given. But then the rule tells me that to get the third term, remember this n, this n, this n, they're all the same number. So if this is a 3 for my third term, that means this is 3 minus 1. So that's going to be a sub 2 plus, this is also going to be a 3. 3 minus 2 is 1. So this is a 1. So this is telling me that to get the next number in the list, I have to add together the 2 previous numbers in the list. I have to add together A1 and A2. If I add those together, it's going to give me a 2. If I think about what to do, if this is a 4, if I think about this also being a 4, 4 minus 1 is 3, so this is telling me I have to take the third term. And then if I do the same thing over here, it's the second term. So I'm adding together the 2 previous terms. So I would add together this 2 and this 1. And that would give me 3. Then for 5, if I add together the 2 previous terms, 3 and 2, I would get 5. So I've got this sequence 1, 1, 2, 3, 5. If I kept going, if I wanted to do the next one, say like a 6, I would add the 2 previous terms together, 5 and 3. So that would give me 8. And this particular one is actually a special kind of sequence. I don't really want to tell you what it is. I want to see if anybody knows what it is. I'll leave a spot on the Google form this week for you to tell me if you know what that sequence is. 1, 1, 2, 3, 5, 8. You can continue on if you want, figuring out the terms. But you just add the previous 2 to get together to get the next term. So I'll leave a spot for you to comment if you can figure out what kind of sequence that is. All right, so we have a explicitly defined sequence, which is just, hey, here's this formula, plug in these numbers, work it out. This is similar. We still have a formula that we're plugging things into for the other, the recursive. We still have a formula that we're using, but we have to know the starting point, right? Because all of these that we did, all 3 of these examples, we couldn't get to the next number without knowing what came before it. So if I just gave you this rule and I didn't tell you like what the starting point was, you would sort of be stuck. You wouldn't really know where to go. So that's the difference sort of in the recursive definition. I'm going to give you a little bit more vocabulary really quick before we move on to the idea of a series. So you will, I'm not going to spend too much time on these words. I'm going to sort of give you the definition, and then I'm going to jump over to Desmos and kind of give you a visual of what these represent. But you will talk more about this concept when you guys get into calculus. So there are a couple of terms that we're going to talk about here. One is called a convergent sequence. So a convergent sequence, if you know what the word converge means it's like coming together. So a convergent sequence is when the terms approach a unique number. A unique number. I don't know what that is. Sorry, I had a little weird thing. A unique number. Sometimes this is called a limit. So if you know anything about calculus, or if you have friends that are in calculus and they talk about limits, this is kind of one of the first things that you'll talk about, not convergent, but the idea of a limit is kind of one of the first big ideas that you talk about in calculus. So this is sometimes called a limit. So the unique number that the sequence approaches is sometimes called a limit. The opposite of that, opposite of converging, is diverging. So you can have a divergent sequence, and that means that the terms do not approach a single number or a single value. So I'm gonna give you some quick examples and then show you kind of visually what that looks like. So I'm gonna sort of give you three really quick ones. I'm gonna give you the rule, and then I'm gonna go ahead and kind of fill in the values for you. So we've got -3n + 12. So this rule that I've given you, this is explicit because I've just sort of given you the definition, right? There's no other information to go with it. So this would be an example of an explicit formula or an explicitly defined sequence. Got another one that we could say like this, and then let's see if you can see that. A sub n is -1/2 times the previous term. So if we think about what kind that is going to be, that is our recursive, because I've given you the first term and then the rule for how to get the next one. Basically, it's telling us to take the previous term and multiply it by 1/2. And then we're going to multiply, or -1/2. And then we're just going to keep multiplying by -1/2. So you can sort of kind of get an idea already of what might happen. So if you say this is our first number, we're going to take 1/2 of that, and then whatever we get, we're going to take 1/2 of that again, and then we're going to cut that in 1/2, and then we're going to cut that in 1/2, and then we're going to cut that in 1/2. So if you kind of think about what would happen to all those numbers as you went along that way, sort of kind of make a prediction about what you think those points are going to look like when we plot those. So I'm just going to, for each one of these, just make a chart really quick. And in the interest of time, I'm just going to tell you what these values are. You can go back and kind of take the time to plug them in if you want, but I'm just going to go ahead and tell you what these are. So all of these I'm just plugging in one at a time. So if I plug in 1, get 12. Hold on, let me call this A sub n. So then we get, let's see, 9, 6, 3, 0, -3, -6, -9. And then let me do this one over here. I'm going to plug in the same numbers. Sub n, 1, 2, 3, 4, 5, 6, 7, 8. So again, think about what's happening here with our rule. We're just taking half of the previous number every single time. So my first term is 36. If I multiply that by -1/2, get -18. Then I cut that in half. And I cut that in half. And I just keep cutting things in half. Also, my sign is sort of oscillating back and forth, positive, negative. I'm rounding a bit for those last ones. So these values in this second column, those are all the numbers in my sequence. Same thing here. These are all the numbers in my sequence. I'm going to give you one more because I'm going to switch over to Desmos in just a second. We're going to look at all of these. I've got these already set up over there. So this one's kind of a crazy one. -1 to the n times n over 4n plus 1. So there's our rule. Again, that's explicit because I've just kind of thrown this rule at you. You don't need to know the previous term. I'm just going to plug numbers in. I'm going to do the same thing. 1, 2, 3, 4, 5, 6, 7, 8. And if I plug numbers 1 through 8 into this guy and work it out, and again, I'm sort of rounding a bit here, 0.22. All of these are going to come out to be very, very, very similar. Negative 0.24, positive 0.24. Okay. So what I've done is I've gone over into my Desmos and I basically put all 3 of these tables in and plotted these as points. So you can kind of see what we mean visually when we talk about things converging or diverging. So the first one we're going to look at is this one. If you just sort of think about this as a function, think about what kind of function this is. It's just a linear function, right? So we know what a line does. It just goes on forever and ever and ever, right? If we were to keep going, this is just going to keep getting more negative, more negative, more negative. If we went in this direction, these numbers are going to get more positive and more positive. Uh-oh, my battery's getting low. And then it would just keep going on forever. Sorry, I lost my train of thought. I'm going to have to go get my cord here. All right, so let me see. Oh, wait, that's not what I wanted to do. I wanted to just make that smaller. Wait, how do I do that? Escape. There we go. Okay, so I'm going to switch off of this and do this. Okay, so now you guys can see this, hopefully. to go back and check. Let me zoom out. Back up here. Okay, so there's our first chart that we made. And there's our points, right? And again, it's just a linear function. So it's just going to look like a line. So I'm going to leave you guys to sit here really quick while I run into the next room and get my charger. I don't want to pause this because I'm afraid I'm going to screw up my video if I try to pause the recording. So I'm going to let you look at this pretty picture for a second and I'll be right back. I'm back. All right, I'm trying to plug in my battery so it doesn't die. Oh. Okay. Oh, this is stressful. Okay, I'm back. All right, so there's the first one, right? So because this is just going to go on and on and on forever, you know, in the negative direction and in the positive direction, if we go the other way, it's considered divergent because it doesn't really, the values don't approach a single number. They approach infinity, right? Infinity, the positive infinity in one direction, negative infinity in the other direction. So this would be an example of a series, these values over here, that diverge. They don't approach any particular value. So if I turn those off, the second one that we looked at was where we were basically just taking every number and cutting it in half each time, right? So if we look at those, this one, let me zoom in on this one a little bit. This one's a little bit kind of hard to see what's going on. But the idea is, if you look at these numbers, they're getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. And they're just going to keep getting smaller, right? They're just going to keep getting closer and closer and closer to zero. Now, they are sort of oscillating back and forth, positive, negative, but at the same time, they're approaching zero. You can see, like, from the top, if I sort of connected these, it would almost make like a curve thing, and they're kind of almost like an asymptote, right? They're getting closer and closer and closer to zero. Same thing's happening on the bottom. They're getting closer and closer and closer and closer to zero. They're sort of bending and curving in towards that x-axis. So this is an example of something that's converging. They're converging to zero. A sequence or a function doesn't necessarily have to converge to zero. It could converge to anything. Any number doesn't have to be zero. This one in particular is zero. But that's sort of what convergent looks like. The values are kind of slowly getting closer and closer and closer to a particular thing. And then our third one, this one was a little bit weird because all the numbers were kind of similar and they just kind of bounce back and forth between positive and negative, right? So there's that one. I'm gonna zoom in a little bit on that. So you can see, oops, it's just sort of going up, down, up, down, up, down, up, down, up, down, and presumably would just continue going like that, right? So that is another example of something that's divergent. Now, I don't know, they're slightly changing in here, you know, I don't know if that's enough to make a difference. But this was sort of provided as an example of another divergent. If it just sort of bounces around and oscillates back and forth and never really, you know, seems to get closer to any particular thing, that would just be a divergent series. And like I said, you'll talk more about these in calculus, but I just wanted to at least kind of throw those ideas out there to you so you can just kind of hopefully remember sort of what those concepts are when you hear them again later on. Okay, so let's go back to this guy. And let me make this bigger. Okay, so now we're going to talk about a series. We're kind of coming down to the end. There's not as much to talk about with series. Series, and then our other topic that was thrown in the heading of sigma notation. These kind of go together. So we get a new page here. And all right, so a series. A series, really the only difference between a sequence and a series, if I took all of those numbers in that sequence, in that list, that all those examples that we just did where we were listing out the first 4 terms or the first 5 terms or whatever, if I took all of those numbers that we got in our sequence and I just started to add them all up, that would make a series. That's the only difference. We're just adding up all the terms. So a series is the sum of all the terms in a sequence. We just add them all up. So again, a series can be finite. A finite series is the sum of the terms in a finite sequence. Makes sense. We have a finite list of numbers. We can add them up. We get a sum. The kind of the weird idea for this one is that you can also have an infinite series. An infinite series. So think about that. A series is a sum, but how can we have a sum of something that goes on forever, right? Like how can we add an infinite list of numbers together and get an answer and get a sum? So we're going to talk about that a little bit later on in the unit, but I'll give you a little bit of a definition here. So for now, we'll just say that this is the sum of the terms in an infinite sequence. And again, that's kind of a weird idea to think about, that the numbers could just go on and on and on and on forever, but we could still add them together and get a sum. But there's a little bit of a qualifier that we need to throw in here, which is that we can only do this, and here's where this idea of convergence comes in that we just mentioned. We can only do this when the infinite sequence converges to 0. So it must converge to 0. So we can only do this with an infinite sequence if the numbers are getting smaller and smaller and smaller and smaller and smaller and smaller. Okay, that's the only time that we're able to sort of add them together, and I'm sort of using finger quotes here. You can't really see me, but add them together, finger quotes, to get an answer. And again, that's going to come up a little bit later on in the unit. We'll sort of see how that works. Another thing to throw in here is the idea of a partial sum. A partial sum is kind of what it sounds like. We're not adding up the whole list of numbers. We're only adding up a partial list of the numbers. So we say this is the sum of the first n terms. So it could be the first 3 terms, 4 terms, 5 terms, whatever. And the way that this you'll sort of see this, it might say something like the 4th partial sum of, and then they'll give you a rule. So let's see, -2 to the n plus 3. So it might say, find the 4th partial sum of this sequence. And so that's just a fancy way of saying, find the first 4 terms and add them up. That's all you got to do. There is another sort of notation that you might see for this phrase right here, fourth partial sum. This is also sometimes noted as a little s with a subscript 4 for fourth partial sum. The little s just means sum, and the 4 tells you how many numbers you're adding up, right? How many terms you're adding up. If we wanted the 10th partial sum, it would be s with a little subscript of 10. So that's just some notation for that. All right. So then the last thing to talk about briefly is something called sigma notation. So you might have seen this, like I said previously, in Algebra 1, maybe. You may actually have come across this in science classes, maybe like bio or chem, or maybe, well, you guys haven't had physics yet, but for my juniors that are out there, if you're taking physics, you might have seen this in physics. But sigma notation is a way, it's kind of a shortcut way of writing or talking about a series when we're adding stuff up. So series are often written in sigma notation. Sometimes this is also called summation notation. You might see that used in a textbook or a website or something in place of sigma notation. So this is the thing that has the big capital sigma in it, the Greek letter sigma. That's the one that looks sort of like a big E, but it's kind of like pointy, sort of. So kind of like that. So what you'll usually see in math when we talk about series, you'll see something like this. And that's our sigma notation. So we have to sort of know what all of these numbers and symbols around it represent. So obviously this thing we've already seen before in our previous example. So this is going to be like the rule or the formula that we're given. And then these numbers down here at the bottom, or this number, that tells you where to start. Like what number do we start plugging into our rule? So this is where we start. And then this value up here, this thing that I've called K, this is also going to be a number. So when we do like a specific example in just a second, this will be a number. And that's the number where you stop. So if this, like this is telling me to start by plugging in a 1, and then I'd plug in a 2, and then I plug in a 3, and then a 4, and then a 5. And let's say this were a 9. That means that I would go all the way up to and including 9, and then once I plugged in my 9 and evaluated that, I would stop. That would be my ending point, okay? So this tells us where to end, okay? And we can't forget that the sigma itself means that we're adding all of this stuff up as we go. So we're finding A1. And then adding that to A2, A3, all the way up to whatever that K value was that was over here at the top. Okay, that's our stopping point. Okay, so don't forget what that sigma means, because I've had students in the past that they know this is the starting value, they know this is the ending value, they know they have to take these numbers and plug them into this rule, and they write them all out, but then they don't add them together. They just list out the numbers. But we have to actually remember that this big symbol, this sigma symbol, that has a meaning as well. It means that we're adding things up. Anytime you see this symbol in math, doesn't matter if we're talking about series, We use it in statistics a lot. Like I said, you might come across it in chemistry or biology or physics. Anytime you see this symbol in math or science, it means that you're adding things up. Okay, you're adding a bunch of stuff together. So to give you an example of what that would look like, let's say we have our big sigma, and we're going to start at 1 and we're going to go to 5, and then our rule is 4n minus 3. So that means I'm going to plug in a 1, see what I get, then plug in a 2, see what I get, plug in a 3, all the way up to 5, and all those numbers that I'm getting as I evaluate, I'm going to add all of those up as I go. Okay? So, and again, I'm going to write kind of this middle part out just so you can have it in your notes if you need to look back at it. But most of you can probably do a lot of this in your head. So, you know, don't feel like you need to necessarily write down every single bit of this. But we would be doing 4, plugging in a 1, and then adding to that whatever we get when we plug in a 2. And then I would keep going all the way up to 5. Okay. So if I go through and I evaluate each one of those, these are the numbers that I get. I got 1 and 5, 9, 13, 17. And again, we're adding all of that stuff up as we go. So we get 45 as our answer. So when you're doing a problem like this, your answer is just going to be a single number, right? Because we're doing a sum. We're adding this up as we go. All right. I'll give you guys one to look at. So here we're starting at 3 and we're going to 7. So keep that in mind. Starting at 3 and going to 7. So you're going to plug in 3, 4, 5, 6, and 7. And then your rule is 6n minus 3 over 2. So again, if you want to stop the video, see if you can work that out, get your answer, come back, I'll tell you what I got. Okay, here's my numbers that I got when I worked this out. I got 7.5, I got 10.5, I got 13.5, I got 16.5, and 19.5. So 3, 4, 5, 6, 7. Yep. And then all that together, 67.5. Those are my values that I got. All right, one little quick last thing. We're going to go the other way. This is, again, kind of like the little brain teaser thing I gave you near the beginning of the video. We're going to be writing things in sigma notation. So I'm going to give you the list of numbers, and then you're going to see if you can figure out what the rule was and then write it as sigma notation. So express each in sigma notation. All right, so we've got 1 plus 4 plus 9 plus 16 and so on. For part B, we've got 1/3 plus 2/4 plus 3/5 plus ... all the way up to 9/11. So notice this one has an ending point. The first one doesn't have an ending point. So you might sort of think about when you're doing sigma notation, if there's no ending point, what do we put on the top of our sigma when there's no ending point? Part C, we've got 3, 5, 7, on and on and on, no ending point. And then for D, we've got 4, 8, 12, 16, and 20, and that's our ending point. So your job, if you want a little challenge, is to think about how do we write all of these with that sigma notation. So I'll give you a hint. You can assume that all of these are starting at 1. That'll be helpful. All of these are starting at 1. But then you have to sort of figure out, well, what could be the rule that goes out here for each one of these? And then we know our starting point, but we have to think about our ending points as well. So you can stop the video if you want and work on these for a second and then start it up again and see if you got the right answer. All right, so I'm going to give you the rules for each of these. So here we're just squaring terms every single time. So this is just going to be n squared. And since this doesn't have an end, we just put infinity up at the top. So this one down here, because it doesn't have an end either. Just going to put a little infinity there. And then let's see, for B, the rule is n over n plus 2. We're starting at 1, and then we would go up to 9. Let's see, for part C, this rule is 2n plus 1. And then for the last one, the rule is 4 times n. We're starting at 1, and we're ending at 5, because 4 times 5 would give us that last number of 20. All right, it's kind of a long video, especially since I had to run downstairs and get my battery charger. All right, so I want to make this go away. Okay, so, whew, that felt like a marathon. All right, so hopefully, if you feel like that was a little long, I felt like that was a little long, maybe longer than normal, but you can like stop and start and do it in chunks. But that gives you kind of a general overview of just the idea of a sequence, list of numbers, and a series, adding them up. So now in the later videos, when we talk about arithmetic sequences and series and geometric sequences and series, hopefully you guys will remember that vocabulary, I hope. Okay. Okay, so that's it for this week. You don't have any extra homework to go along with that as long as you watch the video and then you kind of, you know, worked the problems as we went along the examples. You're good. Just make sure that you check out the Alex quiz. And that's that. I'll still be doing my kind of check-in help sessions if you need to ask me a question or you just want to stop and say hi. I'll be around Tuesday afternoon, so that'll be in Teams. So you can come say hi. Okay, bye guys. Let me know if you need me.